Recording is rolling. It is Friday, January 10. So you guys have your lab pages out from yesterday. You guys remember, and you have all the same lab materials on your desk. Right? So you guys remember yesterday we were doing this torque lab, or we were doing the seesaw version. Right? So you're holding up this 1 meter stick with one spring scale. You had a couple of lab weights on it. The question I had you guys solve was what's the mystery lab weight? Right? Yeah. So see right here it says force right mystery, the force being your weight. Okay. I had you guys solve it two different ways. So the first way we did it on the right side of the page is probably the more intuitive way, which is to treat this spring scale point as the pivot point, right? And sum the torque about that. Because for equilibrium, the torque has to sum to what? 0. And you use that and you can solve the whole thing, just like that. Okay. And then the last thing you guys did yesterday was you had possibly the exact same setup, like nothing physically changed, except your perspective. And then you went from the far end and you sum the torque about that point. Now, guys, can you pick any point in the whole universe to sum the torque about it and it still sums to 0? Yeah, you don't have to pick, hey, the spring scale point is the pivot point, or you can pick like this point, this 0 and a new stick. So that was yesterday. We did all that yesterday. Right. And today we're going to do the other side of the page, right, which is the more scaffold looking setup. Okay. So just to keep the theme sort of the same, I have the same target question is what is this weight? So you'll hang a lab weight there. You'll obviously know what it is, but can you calculate it going through torque specifically? The other way you can solve this maybe through force, say, well, the up forces have to cancel with the down forces, but we have you guys solve it through torque. That's how I laid out this these tables down here. Okay. And then you can check. So if you hang a 10 Newton weight on it and you get, say, like 9.5 Newtons, like, okay, that's pretty close. Right. I want to walk you guys through some examples. So this question here is actually probably more like what you would get out of a textbook or maybe an AP question, which is to know what are the tensions in the ropes. Hey, doesn't this align with the story I was walking you guys through yesterday? You guys remember Paul Hewitt walking around on the scaffold? Okay, so now we got a scaffold. It's got a couple of ropes. Now I'm really simplifying this. You guys see this beam? It says negligible mass on it. Negligible mass. Okay? That's not always the case. You could always make it more complicated. For example, one of your textbook questions is number 22. You guys see this hungry bear walking out towards this basket of goodies? Right. Maybe the beam's walking on has some weight. The bear has some weight. Maybe this basket of goodies has some weight. Right. So it's just a more complex version of this. This is more a stripped down fundamental type version. So this guy's walking back and forth. Right. Maybe this is Paul Hewitt walking on a scaffold, and maybe he has his friend over here like plucking this right in tension. As he walks towards the right, what happens to the tension on the right side? It increases. And if you plucked it, I bet it sounded like boing, 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 boing. If he walks away from it towards the left, you bet boing, 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 boing. You guys can hear that? Huh. All right. So what exactly are these tensions as a function of where he's standing on the beam? So I have him 7 meters over from the left in a 10-meter long beam. And let's say all the weight is just this person here. Let's say it weighs 100 newtons, like a little dwarf person. All right. So it's 100 newtons. Okay. All right. So what could that tension be? Here, I'll walk you guys through it. Now, there are two conditions that you'd want to satisfy. And guys, what two conditions am I thinking of? What's one of the conditions to be able to answer this? Yeah, so equilibrium, right? And for equilibrium, here, I'll even spell it out. Equilibrium. Okay. I want the sum of the forces to go to 0. In this case, they're all vertical forces, aren't they? So I could throw a little subscript y on that force, right? 0 newtons. Okay, because everything's vertical. Okay? And the other condition is the sum of the what also goes to 0. Torque. Yeah, sum of the torque goes to 0. And guys, what's the unit for torque? Newton meters. That's right. Right. Oh, if I heard foot pounds, that's also true. Yeah. And then this class we're using metric, so 8 meters. And true, foot pounds. If you ever hear that, talking about some kind of torque. Okay. Right now, right, so if we're going to stick to clockwise, counterclockwise, that's what AP does. That's what, here, I'll just do with you guys. Right. I have to pick a pivot point somewhere on this beam. Okay, can I pick any point? Yeah, and the torque would sum to 0. Yeah, what do you think?
Wouldn't it just like average out, like if he's halfway through each side would carry 50%? If he's like 70% through, one side would be 70, one side would be 30.
That is true. That's a good shortcut. Yeah. If you guys just heard what Luke said, if he was standing right at the middle, then wouldn't this obviously be like 50-50? Right? It would split. Right. And if he's not standing though, you guys see how I have him like 70% of the way over? Right. So as a good shortcut rule of thumb, do you guys think that the fact that he's 70% of the way over, 70% of the total force, and therefore maybe 70 newtons is on the right side, no, there's on the left. Okay. That does end up being the answer to this question. Now, if you make this more complicated, like if you have the bear in the basket of goodies, or what if I give some weight to this beam, or what if I don't have these tension straight vertical, or there's a number of complexities you can do where maybe you can't run to an immediate shortcut. So you have to use this like this equilibrium method that we're going to do. Yeah, yeah, and yeah. I've got some PowerPoint slides. We'll get some variations on this right in a few minutes. All right. Now, so picking up here. So we could pick any point in sum the torque, and the torque could go to zero. Now here's the tricky thing. I can solve this whole thing actually with just this condition here. This torque condition goes to zero. Okay. If I do that, say I pick like this random point right here. If I take this random point, like middle of the beam, the torque would sum to zero. True. Right. But you guys see how there would be at this point two unknowns if I'm starting from scratch? See, I don't know either of these tensions. Guys, if I set up just one equation, can I solve one equation with two unknowns in it? Is that solvable? Not by itself, no. Okay, so maybe I have to bring in something else. Right? But guys, here's a really powerful trick that almost certainly you'll be able to use on some AP question. When you see AP question, exam today, is if you pick a pivot point that's at the location of one of your unknown forces, then how much torque does that force cause at that pivot point? Zero. Right? Like if I go over here to this door and I start pushing on these hinges, like I gotta get out of this place, pushing on these hinges. Is that ever gonna turn the door? No, because there's no torque there. Right? So as the math trick, I could pick this point right here, bam, and sum the torque about this point. And from this point of view, yeah, the left side just causes no torque, so I can just throw that one out of the equations altogether. Right? And now I'm down to one unknown, which is this this right tension is trying to pull this whole thing which way, clockwise or counterclockwise? Counterclockwise, right? Or if I did that right-hand rule, which you might see in college, I got this R crossed with this F, and the torque would be out of the page. We call that positive torque. Okay? And then this guy standing on the platform, right now, in terms of clockwise, counterclockwise, he's trying to make the whole thing turn which way? Clockwise. Or in terms of right-hand rule, here's my R crossed with F, and now my thumb points down like into the page, okay? Which we're not going to do. AP doesn't do, but you might see college. Okay. And so that's really one way. I can actually solve the whole thing with just this condition right here, this torque. Right. Well, maybe I'll return to torque side. But so let's do sum of torque goes to zero. So from that left point, I got, remember, torque is R cross F. And this radial arm is horizontal. These forces are all vertical. So they're already aligned perpendicular. So that's convenient. Okay. So I got 7 meters and 100 newtons. So 7 meters times 100 newtons, right? That could be, you know what, since that's clockwise, that's, maybe this is negative 100 newtons if it's down. I don't know, one way or another, I'll make it negative somehow, right? Because it'd be clockwise is negative, right? Then plus, now the counterclockwise I'll consider positive, okay? At 10 meters, I got this unknown force TR. So at the full 10 meters, I got TR that I'm solving for, okay? And what does that sum to? Zero Newton meters because it's equilibrium. Okay, so I got 700 Newton meters here. I'll add that over. So 10 meters times tension in the right side equals, and then when I add that over, it'd be 700 Newton meters. Thank you. Okay. Then divide both sides by 10 and the meters. And tension right side is 70 newtons. Yeah, that is 70 newtons. That's right. Right. If that, right. You guys, if the tension on the right side is 70 newtons, maybe I could play off this other condition here. The sum of the forces vertical also goes to zero. Okay. So what have we got? We've got 100 down. We got 70 up here. Therefore, the tension on the left side has to be how much?
30.
The other 30 newtons. There you go. So it's like Luca was saying, a good shortcut is if you have this very simple setup where it's just on the beam. Notice I gave the beam no mass. So after that, the ropes are on the ends. Right. So this guy has all the way. Yeah, the fact that he's 70% of the way over is going to translate to 70% goes into the right side. Oh, yeah.
Because the thing he's standing on has negligible mass, because of that, wouldn't wherever he's standing in, wouldn't it act like a lever and would start like bending up? Like if you stood far enough over, wouldn't it start?
Oh, like if he walked like over here?
Yeah.
Okay. Yeah, that'd be true. Yeah, guys, if I extend this, make this like even longer. Now, let's say he walks past this rope and he starts walking to the right side. Yeah, true. This left side would have to go into compression, which ropes can't really go into compression. So yeah, the whole thing would just start being like that, wouldn't it? Yeah, that's true. Okay, we're gonna ignore that. Okay. All right. All right. So you guys good so far? Okay. We throw a few PowerPoint slides up here. Come on. PowerPoint. Okay. All right. So here's what you guys did yesterday. Okay. All right. So you guys remember this yesterday? Okay. Here's more what you're doing today. So remember, you got two conditions for equilibrium, right? And we just solved this, right? So sum of forces goes to zero. Looks like that. Boink. Sum of torque goes to zero. Okay. Oh, guys, according to this setup, which point did I pick as the pivot point? Because there's lots of different ways I could have written this equation at the very bottom. Do you guys see what the pivot point is according to how I wrote that? Yeah, it's at the point where we're so it's also the far left end, right? Okay. Yeah, you could pick the side on the right side, but okay, but I picked this point here, just like I did with you guys, right? And so lab table, lab table. This is what you did yesterday. Is what you're doing today. Okay, got that. Uh, ooh, now, okay, now there's different variations on this question. Here's a real classic physics question. Uh, I've seen AP ask this. I remember this shows up in my college classes back in the day. If there's a ladder resting against a frictionless wall, this is the full diagram. So here's the force you consider. Now, now you might be asked, like, what's the minimum coefficient of friction? That might be a good question to hold the ladder in place. Or if you knew the coefficient of friction, like, what's the maximum angle theta that you could have where it would no longer, okay, something like that. Okay, keep it in place. Okay. No matter what the question is, a pretty good choice for the pivot point would be, do you guys see all the way down here at the floor where there's two forces acting? There's the normal force from the floor holding everything up, and there's also this friction force keeping it in check horizontally, right? The fact that there's two forces there, if you pick that as the pivot point, that already zeroes out two of the forces in terms of torque, right? So that's a really good choice to start the puzzle. I'll pick that as the pivot point, okay? And then you can solve the whole thing from there. I got some equations here. Okay. Ooh, this looks a lot like that hungry bear trying to walk out and get the goodies at the end, right? Doesn't it? Straight from your textbook. Okay. I think I've seen AP ask variations on this one too. Here, here's the setup. Here's a nice equation down here we can solve. Right. Maybe the question could be, what's the tension in the cable? Right. That could be a good question. Okay. Right. Okay. The rest of these are getting into angular momentum, so I think I'll save those for a different day because we got to get you guys going on this lab. So let's go back to okay. This right here is going to be pretty much your lab today. Bump this. Right. All right. So we find that. So this is your guys' think lab right here. All right. So similar to yesterday, you can have one single setup, and I'm having you guys do two different perspectives of how you go about solving this. Right? The goal is mystery weight, just like yesterday. It was mystery weight. Right? I mean, obviously you're going to know whatever you hang on it. So if I hang this on it, 500 grams, guys, 500 grams. You guys know weighs how much? But so it's like 5 newtons, 5 newtons of like weight, right? Okay. But let's say it was like wrapped in paper and you didn't know what it was. You just have it hanging there or some mystery object, something like that. Right? Okay. Okay. So, can you solve that with torque? And I'm giving you guys the points to try. So the first way, how do you guys do it? Down the right side page says pivot point left side. Left force, which is bam, that right there. I just put an X on it. What the pivot point could be. You see right there? Okay. And the advantage of picking that point is that whatever the left force is from that spring scale causes zero torque about that point. So it simplifies the equation. Right? You can solve it this way. Okay. And the very last box is going to be what is this force right here? So from this point of view, I got the meter stick pulls a little bit clockwise. Oh, here, I'll give you the weight of the meter stick. You guys remember what it was yesterday? Yeah, 1.2 newtons. Okay. And then, plus or minus a little bit, but we'll round it. Okay. Okay. This weight, this mystery weight, is definitely pulling clockwise, and this right spring scale is holding everything in check counterclockwise. So I see those three torques relative to this point. Okay. The other way you can do it, you don't have to physically change anything, but you will be changing your perspective, is 0 centimeter mark, kind of like yesterday, which is really just a random point. So if I sum the torques about that point, okay, well, now it looks a little different because now this left spring scale is pulling counterclockwise, and then the weight of the meter stick is a little bit clockwise. this weight causes clockwise and this other spring scale causes counterclockwise relative to those 0 centimeter mark. Okay. All right. So I'm gonna walk around today, help you guys out. Ooh, yeah, we got what 20 minutes almost to do this, right? And then just turn this page into the gray tray, and I will give you guys lab points.